Hello guys, welcome to the last class of the semester. So if you remember in the part 1 of the video, or part 1 of the numerical differentiation and integration, we were discussing about integration. We talked about actually the difference between numerical computing and symbolic computing. So we also established the two different formulas or three different formulas for numerical differentiation. The first one was the 2-point forward difference formula. We did one example, if you remember. So in this, we also established, or we defined the 3-point center difference formula, and this is the one. And also we did one example of this. So in general, we established that we can develop higher derivatives just using the same procedure that we follow to develop the first formulas and the Taylor expansions. Of course, we have to remember that we have to be able to deduct the error terms at the end of the series, and somehow for the second derivative, we actually had the 3-point center difference formula that we already deducted here, and we also apply an exercise using these two different equations, if you remember, the two different formulas. And then we went and did one example in Excel, and this is what we obtained at the end using different values of h. If you remember, at that point, we said that sometimes the use of h is not as efficient as we are expecting when decreasing it. So we realized that when we have a value of between h equal to 10 to the power minus 4 and 10 to the power minus 6, I think it was the most efficient value of h to obtain a very small error, in this case for both formulas. So the error was very small, and then we saw that the error increased somehow when we reached 10 to the power minus 8, which is actually a problem that we obtain here when we decrease these numbers. If you remember, here we have the effect of subtracting very similar numbers, because h is going to be almost the same, and then we have also the effect of dividing by a very small number. So those things in a computer actually causes some trouble. Okay, we also, if you remember, had a brief tutorial of the MATLAB symbolic differentiation and integration, and it's of course in the video of the previous class. You can watch the video and then you can just go through the tutorial once again. Okay. So now, today we're going to actually start with the Newton-Cotes formula for numerical integration. We already know how to actually differentiate a equation or based on a interpolation formula or interpolation function. So we actually calculate the derivative in these examples, right? Using a specific formula. Some of the cases, remember that we can find the derivative, but sometimes we cannot find it. So we have to use the approximation as we develop this. This later will be used in the finite difference approaches. However, this is beyond the scope of this class, and we will finish here. And remember, next week is the week to actually catch up with the assignments. So don't miss that opportunity to actually turn in the assignments that you missed throughout the semester. So following the Newton-Cotes formula for numerical integration, so the numerical calculation of definite integrals relies on many of the same tools we already saw. Of course, if you remember, we based our approximation of data sets of points using interpolation. We already know about Lagrange interpolation, Newton divided difference, and we also use splines to approximate the functions. Also, we use least square modeling to approximate certain model to fit some data, given data. Okay, so we have alternatives. And then once we have the interpolation polynomial or the splines, we can actually integrate, which is just the area below the curve. Now, in this class, we're going to discuss methods for numerical integration or quadrature. The same thing, and we're going to use the tools that we already saw in previous classes. For example, if we actually define a function f on the interval a and b, we can obtain the interpolating polynomial throughout the points that we are given, and then it is just very simple to evaluate the integral using a polynomial, and this calculation could be used to compute the area under the curve. Okay, for this purpose, we have to define first the very basic foundation of the integration. With that in mind, we are going to start with the Newton-Cotes approaches. So, and these are very basic shapes of, I would say, like of small integrals or one interval integrals. And we will actually find a low degree approximation using the least square for the first approximation. Sorry, the polynomial for the first approximation, and also least square when we move to some other complicated steps, and we're going to use the Gaussian quadrature. So this is actually the Newton-Cotes formulas. So for the first one, of course, we can see that the purpose of an integral is to calculate the area below the curve. So if we actually pay attention to these plots, A, B, and C, we see that in general they're based on certain ranges. So the certain ranges are actually based on in h distance, which is actually on the x-axis. And we also base on the y-axis, but the y-axis is only actually limited to 1. So why we are limiting this to 1? Because if we limited this to 1, we are going to be able to use it for any type of height when we move to a more complicated integrals. So for example, here we see that we are using a very basic form, which is a triangle. On the second figure, we see that we're using a parabol. And then for the following, we are just defining area under a different approximation curve. Okay, so to actually just have a very quick integration over this formula. So of course, in this case, we are describing an integral ax divided by h, which in this case is h is just identified by the width of the base of the triangle, and x it's equal to the component that we have here. So of course this is going to be the ratio of x and the x to h, so that we are going to obtain the area below the triangle. And the area below the triangle, because this is equal to 1 in general, if we just fix it to this width, so we are going to realize that this is equal to h divided by 2. Right? So this is a very simple approximation once we integrate this expression, assuming that h is going to be constant and x is of course going to be the distance over the x-axis. So the second figure, we see that we have a more complicated integral, but this is actually pretty much what we did before when we moved to a parabolic interpolation. Remember, we have 3 points where in general the base of the parabola or the width of the parabola depended on certain width. In this case, the width is equal to minus h to h. So we have this width, and then we also have a height equal to 1. So once we obtain this interpolation polynomial, so we will see that this integration is equal to x minus x cubic divided by 3h squared. So and once we substitute, we evaluate the integration over this interval, we see that is 4/3 of h. So this is the area of a parabolic function, as long as this kept the height equal to 1 and the width equal to h, or half width. Okay, so then we have, additionally, we have also a problem where we have a more complicated polynomial scheme, and then we just for simplicity, I won't explain this one, but in general, we obtain that this is 1/3 of h. So this is what we're going to be doing. We're going to be doing in some complicated matters. This is going to be solved by could be solved actually as a trapezoid value once we actually move this to higher values. This could be solved by a Simpsons rule, the Simpsons rule of integration, and then this is actually a mixed or a composite approximation of these two formulas, or these two components. Okay, so we're going to see this actually later on, but we're going to start with the easiest one. The easiest one in general is the trapezoid rule. So we begin with this application based on an interpolation of a trapezoid. So in general, if you think about it in the figure A, so we have a shape of a certain curve, and then we approximate the area below the curve by a trapezoid shape, or trapezoidal shape. So, but in general, we'll see that we can have actually a very big error if we actually use a trapezoid for this area, because we have a big chunk of the area here above the curve. So this probably wouldn't be the best option. But this is just for the simplicity of the method, to actually be able to define the range of the equation. Okay, so in general, so this is the simplest approximation because we are only using 2 points. We're later going to discuss this one once we reach the Simpsons rule, but in general, this is what we have here. It's an interpolation between 2 points, and of course is between a certain range or width, which could be equal to, in this case, x0 and x1. And of course, we have to denote that the values of y0 is equal to the function evaluated in x0 and the function evaluated in y1, respectively. And of course, this function is equal to, in this case, to a function that is going to be declared as a line. So it's a line. In this case, it's going to be a parabolic expression, but in this case, it's just a very simple line. So if we consider 1 degree interpolating polynomial P1 to the points already given, x0, y0, and x1, y1, so we are going to obtain the basic formula for the trapezoid rule. So this is what we get if we're using the Lagrange interpolation. Remember, we have the Lagrange interpolation. That is basically also, we go back again to the Taylor series. So we have the Lagrange is equal to the first point times x minus x1 and divided by x0 minus x1. And of course, the second point on y, it's the same thing. y1 is equal to 1y times x minus x0 divided by x1 minus x0. And of course, we have at more higher degrees, higher order terms here that is equal to this 1x x minus x0 times x minus x1 divided by 2 factorials, and then the second derivative. But assuming that we do not have the second derivative in these cases, or we might not have it, so we can actually split this term of this interpolating polynomial into different sections. So for this one, we have the polynomial expression px, and this term is actually the error term. Okay, we have to remember that this actually series it's continuous, so we can have higher degrees. But for these cases specifically, we are only using one term that characterizes the error. Okay, and of course these values of the value of the cx or the cx, it's of course depends on a continuous space of x. So it has to be in between the 2 points because that's the purpose of the Taylor series, right? So we can integrate then both sides of the equations or the integrals. So we have that the integral of the function f(x) could be approximated by the integral of px in the intervals from x0 to x1, and the error term as well for the same interval. Okay, so with that in mind, so we can actually substitute the Lagrange terms, and we are going to obtain something similar to this one. So for the first integral terms, that they are these two terms, so we have this integration. And of course, this integration is as a function of x. These x1, x0, and x1, remember, there are actually points already given. So if we have points already given by an expression or by certain interval that we selected in x-axis, so we can actually obtain the integral very easily. So I won't develop the integral because this is a very simple integral, but I'm going to give you some tools to verify actually this kind of terms. So what we do here, so just imagine for a moment that x is actually the actual variable. We have a, which is equal to x1, and we have b, which is equal to x0. So the formula, if we want to integrate this one, so we'll actually be able to be integrated using this type of expression. So we have that xa minus x minus a divided by b minus a is going to be our solution. But just give me a second. So if we have this one, so we can actually develop this formula, and then so we'll see expanded forms. Is this integral? Hold on, give me a second. I don't know if this is integral actually. So, oh, this is not the one I was looking for. Give me a second. So, integral definida, we can actually put it like this. Wolfram mathematical. So we'll see. So I think this should be the one. Yeah, this is the one. So for example, if I say that I want x minus a divided by, I'm going to make this bigger, is going to be b minus a, and then the interval is going to be from, if you think about this one, is going to be from x0 to x1, so it's going to be from b to a, right? From b to a, if I'm correct. And then we calculated the formula right here. And then the definition of the integral would be a minus b divided by 2. So if we actually go here, so we can see that the expression of this one is actually a minus b, but we are replacing the value of h as the x1 minus x0, which is actually a minus b. So it would be the integral, because this is a constant of a minus b, or x1 minus x0 divided by 2, which is what we already obtained on this integration. Okay, so no, this integration. So this integration. So it's a very simple and straightforward actually integral, and you can actually do it at home if you want to do it. You want to validate these formulas, but I'm just showing you to validate this type of integration. So the same for this one, but in general is going to be, instead of we can actually integrate for saying that this is equal to a, this is equal to b, and this is equal to a, and then we obtain the same. But in reality would be that we just gonna use the same x1 minus x0 right here. So, and then of course we see that we have a common term here, so we can factor out h divided by 2, and then we obtain this integration for the first term of this formula. Okay, so the only thing that we need to do, well, I already do, As already did, actually h is equal to x is equal to, sorry, h is equal to x1 minus x0, and this is the interval length to compute the integral using the first formula of the Newton Cotes approach. Okay, so this could be validated very easily if we actually go from one value to another one. For example, if instead of going from x0 go to x1, we decided to go from h to 0, this is going to be actually as inverted from negative signs. So from h to 0 is going to be negative signs. So we actually assume that this is going to be minus w, which is equal to x1 minus x. In this case, sorry, to x minus xi, which is the formula. This is going to be the integration, and then this is going to be x1 minus x0, which is already defined here. And in the integration, which is negative because we are inverting the sign of this integration if we are actually at this point. So we can do it in different ways. So we assume that these are going to be equal to the same integral, but in the other side of the quadrant. So we have 0 and h, and then we can easily integrate this formula, and then we see that once we substitute the limits, both of them are going to be equal to h divided by 2. Okay, so be aware of that this is just a very small complication, as long as minus x, w is minus x plus x1, which is practically actually here the opposite, of course, of this. That's why it's actually negative. And then if we actually do it like in the inverse way, so we're saying that w is x minus x0, sorry, we can actually apply it for the second term, and then we do the same. So w is going to be x minus x0, and then x1 minus x0 is going to be equal to h. And once we perform the integration and evaluate in 0 and h, we'll see that this is h divided by 2. So it means that no matter what, if we actually are in the first or the second approximation, so we can obtain the area equal to h divided by 2. Okay, so it's exactly the same what we're doing here to corroborate the formula. Okay, so in general, we have we already developed the integration of px, but we need to develop the integration of the error term. So the error term, as I said, is actually equal to this expression, and it can be simplified to the integration of this, because we have the 2 factorial as a factor, okay, a constant, and the 2 factorial, of course, it's very easy to define, which is equal to 2. 2 times 1 is 2 factorial, and then this is going to be a constant. This is going to be a constant, so it's going to be out. And then we have these 2. And then if we establish, instead of going from x1 from x0 to x1, we say like we're going from 0 to h. So we are assuming that x0 is equal to 0. So this is going to be equal to 0. And then we just established that h is equal to 1, x1, sorry. And then if we assume this one, we can actually change the variables where u is equal to x, and this second term is times equal to u minus h, which is equal to x1. So, and then it's integrated in terms of the u. We integrate this one, and then we evaluate it in 0 and h, and we obtain that the error term is equal to minus x cubic divided by 12 times the second derivative evaluated on c. So, as a general rule, then we say that the trapezoid rule is equal to this expression. So the integration of the function, the numerical integration of the function of x from x0 to x1 is equal to h divided by 2 times y0 plus y1 minus h h to the power 3 divided by 12 times the second derivative of the function evaluated in C, where, of course, h we said is equal to x1 minus x0, and z is between x0 and x1. So this is actually, this has to be met to be able to be an effective integration. Okay. So this is what we have for the trapezoid rule. So now we're going to move to a more sophisticated approach, the Simpsons rule. So in this case, we now are actually assuming or picturing this procedure using this figure B, which is actually a parabolic condition. So it's actually the same thing as the trapezoid rule, except that now the 1 degree for interpolating formula is replaced by a parabola, which in general is actually a higher degree interpolation function. As before, we can write the integral effects of the integrand of fx as the sum of the interpolating parabola and the interpolation error. So we already went to this. When we have 3 points, of course, the Lagrange terms or the Lagrange function is going to be equal to 3 different terms, which is based on 3 points, x0, y0, x1, y1, and x2, y2. So these are the three basic values from the Lagrange interpolation, and we already know how to do this. And then we have the error term, which is equal to this expression evaluating in the third derivative of the function. Okay, and then we have it here, and then we do exactly the same as we did for the trapezoid rule. So we are assuming that the x0 to x1 is equal to the integration of the formula fx from x0 to x2 is equal to this. The integration of the polynomial, the interpolating polynomial, and then plus the integration of the error. Be aware here that you have x0 and x2 as a limit, so you do not have x1. So x1 is between x0 and x2. In general, if we run the integration as we did for the trapezoid rule, so we are going to obtain that the first is equal to y h divided by 3, the second is going to be 4 divided by y1, it's equal to 4h divided by 3, and then plus y2 h divided by 3. So this is the integration, and I won't actually do it, but you still can use the formula I'm just giving you here. So just remember that these A, B, and C are the values already given in the interpolation formula. So if you remember here, well, h, we have to compute here h, but it's just as the same as putting this as x minus a times x minus b, and then this is going to be divided by c minus a times, you will have, this is c minus b. Then we have this one, and then the integration is going to go around from b to c, right? From b to c, and you can calculate it. and then the integration is this one, but in general it's pretty much the same. We just have to actually define h. You see, this is what we are obtaining. Okay, so we will define h in a second, but this is what we are just going to obtain. So if you think about it, so it's actually pretty straightforward, and then we just have to run the same thing as we did here for the error term, and then the error term is equal to this one. Okay, so in general, then we define the Simpsons rule as this expression from x0 to x2, and then fx divided by, the integration of the function from x0 to x2 is equal to h divided by 2 times the polynomial, in this case y0 plus 4y1 times y2 minus the respective error term. But pay attention here, this is very important, because here you have that h, that's why I'm defining here, this part. H is equal to x2 minus x1, and this is going to be equal to x1 minus x0. And c is between x0 and x2. You are evaluating from x0 and x2, but the distance from x2 minus x1, which is this one, to the lower part, and then from this one to the upper part, so it's going to be at halfway of these two intervals. So this is going to be divided the halfway between x0 and x2. So that's where it's going to be x1. So if you actually use this definition here, this is as we had like b minus a, and then this is going to be, these are going to be equal to a minus c. Okay, in case of you using actually this formula, which is equal to this one. So you can actually substitute it if you want, and you will find that the formula equivalent for this one is actually this part of the equation. Not the error term, but this part of the equation. Of course, we can see also that we have the fourth derivative for the error term. Okay, so this is very important because we need also to identify that this one sometimes is not available. And if it is, so we have to be able to that the formula or the expression that we want to do is that we want to calculate as an approximation, it has to be able to have the fourth derivative, continuous derivative. So let's go to an exercise, a very, not simple, but a very illustrative exercise. So we need to apply the Trapezoidal Rule and Simpsons rules to approximate this expression. So if you see here is actually the integral of the natural log of x dx. So of course, it's asking us to find an upper and bound for the error in your approximation. So what it's asking is to actually give an error from the left and from the right sides of the approximation. If we use the Trapezoidal Rule, which is this one, Trapezoidal Rule, this is the first thing that we can do, and then this is the second one for the error. So if we use this one, so right here we have that using the Trapezoid Rule, we have this integral can be approximated by h divided by 2, times y0 plus y1. So let's just actually work on this one. So this is going to be the distance between h is going to be equal to, according to this rule, is going to be x1 minus x0. So x1 minus x0 is going to be equal to how much? To 1. So we have 1 and then divided by 2. And of course, y0 is equal to what? To the natural log when x is equal to 1 plus the natural log when x is equal to 2. So they just actually go and simplify this one as a multiplication, and then you have the natural log of 2 divided by 2 is equal to 0.3466. Let me just corroborate that expression, and then the natural log of 2 divided by 2 is equal to 0.34657. So it's actually what we are showing right here. So moving forward, we can also estimate the error for the trapezoid rule. So the error term is equal to this. So it's actually minus h cubic times the second derivative divided by 12, where c, it's in between 1 and 2. Okay, so if we actually want to simplify this one, because h cubic is equal to 1, h is equal to 1, for this case specifically, h to the power 3 is going to be equal to how much? 2 minus 1. And then this is going to be x squared, right? So if we think about this one, so well, assuming that the second derivative, of course, is equal to this one, the magnitude of the error, if we have it here, is going to be equal to 1/2 of this one, right? Because we have here 1/2, which is equal to 1, and then you have the derivative, which is going to be 1/2 of 1 to the power 3 divided by 12 c squared, which is in general the case for this polynomial or the second derivative of the function. Okay, so we compute the error, and the error has to be less than 1/2, which is approximately 0.0834. Okay, in other words, we can say that the integration of natural log of x with the limits from 1 to 2, it's equal to 0.3466 plus minus 0.6834. Okay, this is what we are expecting here. So this is the trapezoid rule. Then if we actually move to the Simpsons rule, we can actually obtain it. But I would like to first obtain the real value of the integral, because this is actually for demonstration purposes. We can obtain the integration. Okay, if we obtain the integration of natural log of x, this is going to be equal to what? To x, well, this is by default, remember, a formula. So the integration of natural log of x is equal to x, the natural log of x evaluating from 1 to 2 minus integration of the x. In this case, it's going to be, this is the formula we have here. So then, if we evaluate the limits, it's equal to 2, which is the value of x, and the upper limit log of 2 minus 1 log of 1 minus 1, which is the integration of this one, because this has no limit. And then this is going to be equal to 0.386294. So, and then if we compare this real value with the value we obtain, we have certain error. We have 0.3466, so it's between the error, because if I add 0.3466 plus 0.0834, I got 0.43. So 0.43, which is actually, this is in between this one minus this one and this one plus this one. So it's actually accurate because it's inside of the bound of we compute for those values. Okay, so it's okay, it's well computed. And now then let's move to the Simpsons rule and see what we get. So first of all, we have to remember that the Simpsons rule is equal to this. So h divided by 3 times y0 plus 4y1 plus y3, and then this is the error term. Okay, pay attention that we need the fourth derivative here. So if we actually move to the Simpsons rule, so we obtain here that this is from 1 to 2. And remember, this formula is the one that holds. And remember that h for this case, because we have a value or a distance between 1 and 2. So this value have to be in between. So for these cases, the value of h is no longer equal to 1 because we have a value in between. So, and then this has to be 1.5 here, and then this has to be in case of 2 minus the upper limit is going to be 0.5, which is minus 0.5 is going to be 1.5. So the distance between this point and the middle one and this point and the middle one is equal to 0.5, which is consistent with what we said here. So here we are actually computing the distances between x2 minus x1 and x1 minus x0. So x0 is equal to 1, x2 is equal to 2, and then to be able to calculate h, we have to find x1. So x1 for both to be true has to be equal to how much? To 0.5, right? So if you think about it here, then we have that x2 is equal to, in this case 2, minus x1, which is 1.5, is going to be equal to 0.5. And then the same for this one, 1.5, this is going to be 1 minus x0. x0 is equal to 1. This is going to be 1.5. And then this is going to be equal to 1. And we have 0.5. So we're just solving this h value so that h for this second case is equal to 0.5. Okay. And then we have that this is going to be divided by 3. Natural log y0, natural log of 1. And then we have 4 times natural log of, in this case, y1. So how much is y1? Of course, is 3 halves because it's the half point between 1 and 2. So 1.5. And then y2 is equal to natural log of 2. So we obtain that this is equal to 0.3858. Okay. So if we want to compute the error, we do it again. And then we obtain them for the Simpsons rule using this value, which is actually this error term. So we already know the value of h, which is equal to 0.0 for both of them, and then divided by 90, and this is to the power 5. So this is going to be the real value, but because we do not have the value of c, well, we have it, but we just assuming here is actually equivalent. And then this has to be equal to 1 divided by, if I solve this expression, is equal to 6 times 0.5 to the square divided by 90. This is going to be equal to 6 to the power 5. Sorry, I made a mistake here. This is going to be equal to 0.00000, well, 0.0021. So that's the value I was expecting. So it's very easy to corroborate, just follow the calculator. And that's it. So I hope you are not having any question, but I will be able to answer it once you're in the class, or you can send me to WhatsApp and I will answer the questions. So let's continue with the class. So you see that the calculated error is very simple here. So you're just using this expression to calculate it. So here you have the value of this one. The second derivative of this is actually equal to 6x squared. Fourth derivative, sorry. And then you have it substituted in this case. And that's pretty much what we need to get for these values. Okay. So let's move to what the Simpsons rule says. So if we are just computing the term, so we say that we have the 0.3858 plus 0.0005. And if you remember that the real value is equal to 0.3862. And this is 0.58. So it's 0.3858 plus 0.0021. This is going to be equal to 0.3879. So, and this value is greater than this one. right? So we are saying that we are actually still in the range of this condition or this interval, right? So which is good. So now we are inside of the interval plus minus this value plus minus 0.021. So that's essentially the very brief explanation of two important rules of or two important methods inside of the Newton-Cotes approaches. So we now know the Trapezoid rule and then we know the Simpsons rule. Okay, and we saw the application in this exercise very quickly. However, remember that if we go back to this picture, we said that this might not be actually the best case to approximate the derivative of the integration of this curve. Why? Because you are just assuming that this is actually straight between these two lines, or even if you actually approach or take the approach of this parabola, so you are still probably approximating kind of good this part, but then you're missing a lot of this part, or you're overestimating this part of the expression. So that's what we don't want to, okay? So we want to have a better approximation, and to be able to approximate that one, we can have three for the parabola case, Simpsons rule, x0 and y and x1 and x2, but then in general we can actually make something like a composite Trapezoid rule or a composite Simpsons rule, and we can actually do it like that. So we move to now to the composite Newton-Cotes formula. Okay, so once again, the limitation of the trapezoid and Simpsons rules is that they are limited to operate on one single interval. So that sucks, right? Because we want to use it for a more complicated shapes or more complicated functions. However, we have the advantage that the integrals or the definite integrals are additive over subintervals. So we can evaluate an integral by dividing this the big interval over subintervals. So we can divide what we have already defined by interval A and B. We can divide it into several subintervals. And then we can calculate an integral by dividing the interval up into several subintervals and then apply the rule that we already know, the rules, the Trapezoid rule and the Simpsons rule separately on each one, and then we just add it up or add them up. So that's would be the strategy to follow when we want to actually apply the composite Newton-Cotes formula. This strategy, of course, it's called the composite numerical integration. Okay, and actually I don't remember if we say this composite or composite. I don't remember, I think it's composite. So the composite trapezoid rule, to start, is simply just the summation of several trapezoid rules approximations. And we, of course, we're going to have adjacent subintervals or panels. So that's what we call. So in general way, we can actually approximate the integration of the function fx in the interval a and b, considering a space grid. In this case, A, which is the maximum interval right here, A here, and B, this is the interval. So it's going to be divided into several steps. So if we actually start with A, x0, which is what we already know, is going to be less than x1, it's going to be less than x2, and it's going to be less than following x minus m minus 2, and so on and so on and so on. However, B has to be in the other way around. So xm has to be greater than xm minus 1, sx minus 2, and then and so on and so on and so on. Okay, so these are the extreme values, and then we are just dividing into several steps. So if you see here, so the horizontal axis, it's characterized with h, with the same type of width that we were using before. So h is going to be xi plus 1 minus xi. That's going to be the h value. Okay, And then this is going to be applied for each I, as we can show in this picture. So if you see here, we have the same equation, the same thing that we have here in this expression. But this is actually a very bad approximation. So we need to improve it by dividing this curve in subintervals. So what we can do then is to take it and then dividing it in subintervals. 1 interval, 2 intervals, 3 intervals, 4 intervals. So pay attention of this. So the extreme is actually x0 and xm, or a and b. But we have there inside several subintervals, and they also overlap. So for this area here that we compute here the area, then for the second one we are overlapping in this point, and in this point. Okay, so that's a something that we have to consider. So, but then first we're going to move to this approach, and then we move to the composite Simpson rule. Which, of course, if you see the picture, it's a better approach than this approach. So it's better to use the Simpson approach, which includes 3 points, and it's additive, than just using trapezoids. Okay, so if we still keep our attention on the composite trapezoid rule, we can actually make the approximation with their term like this one. So it's exactly the same thing that we're using here, that we used before, sorry. H divided by 2 times fxi plus fxi plus 1, and then minus the error term. So it's exactly the same expression we used before. However, and assuming that the second derivative is continuous, we have to add up all the intervals. And if you think about this, so it's not the same as, well, if we see the extremes, the values of this here, so it's okay, it's fine. But then we have inside of the subintervals that are actually overlapping. So that's why we have to consider 2 times this addition, because we have these this height actually repeated twice. That's why if we want to actually add this up in several intervals, so we just have to actually modify this expression in the summation form. So x, the value, or the integral of fx in the interval a and b is going to be equal to h divided by 2 times the function evaluated in a plus the function evaluated in b, plus, here we have the important part, twice the summation of 1 to, from 1 to m minus 1. If you think about it, m minus 1, why m minus 1? If we see that we have 4 subintervals, 1 panels, 1, 2, 3, 4. So it's actually, we are just considering 1, 2, 3 subintervals, or the ones that are repeating twice. So that's why we are saying that we need n minus 1, because we only have 1, 2, and 3 repetition, or overlapping in subintervals. So that's why we have to make the summation from I to equal to 1 to m minus 1 of the function evaluating each of the i's, right? So, and then we also have to characterize the error term, which is also the summation of these 3 points here. This is the error, because this is essentially just located at the limit point, so we don't have to consider the error in this part, on this part, because this is actually okay. But we have to consider the error for the subintervals, or the inner subintervals. So we write it like here, but if you think about it, this is actually a kind of like an average way to do it, but this is n times this one, because this is the summation of this formula over this thing. So it's actually m times the same thing. So we simplify it then as h cubic to the power 12, sorry, divided by 12 times m times the second derivative. So it's actually the same thing, because you are just actually adding 3 times the same thing. is is the same as 3 times the same thing, right? So that's what we have here. So in general here, pay attention. Aquí, here we have actually a different way to define the subinterval. So if we check this out, so the space between the values, the space h is equal to b minus a, b minus a, divided by the number of panels. That would be the h. So, and then if we simplify mh, is going to be equal to b minus a, right? And then the error term is going to be equal to b minus a, because we can have this actually simplified version of this, h squared, right here, well, because we have mh here. So if we have mh here in this one, so we can actually subtract, m is disappearing because we are assuming that mh is equal to b minus a. And then we decrease one order because m includes h, multiplying. So this is actually saying that we have b minus a times h squared times the second derivative divided by 12. So that would be actually a simplification if we analyze the width of the interval. So remember, h is equal to b minus a divided by m, which is the number of panels. Right? So then we can summarize, in this case, if we have a assumption of the second derivative is continuous on the interval a and b, then we have a general rule for the composite trapezoid. So this is what we have. Here we have the approximation and the error term. And then h, pay attention, h is going to be equal to b minus a divided by m, where m is equal to the number of panels. And c is, of course, between a and b. Okay, so be aware of this thing because it's important to be able to characterize the main terms and also the approximation terms and the error term. So pretty much the same what we did here, we can actually apply it to the composite Simpsons rule. So what we do is it's the same strategy. We define evenly spaced grid right here, same condition that we already have here. However, we have an important thing. So here is actually an interval that it's actually in between the 2 points of the points that define the intervals. However, here we have something different because we have x0, x1, x2, and then we have x2m minus 2. Why? Because we have points in between the intervals, right? So we need to also account for those intervals or small intervals in between the two main subintervals. It's like here, so you have 1 point here, 1 point here, but you have one point in between. One here, and then you have 1 point in between. So the same for this one. So 1 point here, 1 point here. Well, they miss 1 point here, and then you have the same for the last one. But this is exactly what we have here. We have to account for the points in the middle, and all these points are defined in the horizontal axis or the x-axis. And then h is going to be exactly the same thing. xi plus 1 minus xi for each of the intervals defined in the interval AB. Okay, as I said, on each length 2h panels, which is actually x2i comma x2i plus 1. For I from 0 to n minus 1, a Simpsons rule has to be actually defined or carried out to be able to have this summation of the integral. Okay, so in easy words, the integral or the integration of the function of x is approximated on each subinterval by the interpolating parabola that fits at x2i comma x2i plus 1 and x to I plus 2. So we have 3 points. You see here, this is the one, the one on the left, the one in the middle, and the one on the right. So we have to sum, and at the end we have to sum up all these 3. Okay, so that's what we have to do. Then the approximation with the error term on each of the subinterval is going to be equal to this. We have it here. The integral, the function effects on from the interval x2i to the x2i plus 2, we have this one, and it can be defined as we did before. If you remember, this is the Simpsons rule right here. Just this one. So it's exactly the same here, exactly the same. This part and this part. So we just move to a more sophisticated approach. Right here. So here we have it, and then we have FA plus FB, which is actually defined in the previous example. However, here we have to also overlapping terms. So, and if you think about the overlapping terms, we have 2 overlapping terms on each of the interval here. But then you have 4 overlapping terms because you have also one here in between these 2. So we have 4 overlapping terms here. So that's why we have to define 4 overlapping terms in x2i minus 1, and then 2 overlapping terms on the fx2i. Okay, this is important to account. If you see these for 4m, of course, we are just having exactly the same number of panels. But here we having actually the one in between, because if you think about it, so you see here we have actually 4. We have 1, 2, 3, 4. But if you analyze the point in between, we have 1, 2, 3, and 4. So 4 overlapping terms here, which is the point in the middle. But we have 1, 2, 3 in this case that are overlapping, and this is the case for those. Right here. So right here. So we have here. And then we have n minus 5, which is equal to 3. Or in this case, when we're defining m equal to 4, as in the figure in the example. So this is actually have to be taken into account. And then, of course, we have the error term, which is the summation of all the errors on each of the subintervals. And this, as I said, can be simplified because this is still the same thing. So this is an addition of, or a multiplication. Well, this is an addition of the fourth derivative in C, but we see that this is equally to m times f, the fourth derivative in C. So it's exactly the same because these are the same derivatives of the function. So it could be simplified like this one. And of course, the interval is still for some A for some C between A and B. And then we have the same addition. So here, since the value of m could be simplified as this one, 2mh divided is equal to b minus a. Why? Because h now is equal to b minus a divided by 2m. Why 2m? Because we have subintervals. We have one subinterval or two subintervals inside of each of the main points. So we have here, if you come here, you have one subinterval inside of one of the interpolation polynomials. So we have 2 of them. So that's why we are assuming here that we have 2 subintervals, 2m. So then we can do exactly the same as we did for the trapezoid rule. We simplify b minus a h fourth. If you see here, still the h decreases 1 term because we have 2mh, right? And then because this is going to be 290 times 2 is equal to 108. 80, sorry. And then this is their term. And then assuming that the fourth derivative is still continuous on the interval a and b, we have the general rule, which is this formula here, minus what we just defined as the error term right here. So this is in general, this is what you're going to be using, this composite rule and this composite rule. Okay, so but let's apply this one because we need to be able to apply it physically. So then we're going to still be using the same thing, but now we're actually defining the same interval, but we are defining 4 panels. So we have 4 panels here. So we need to use both the trapezoid rule and the composite Simpson rules. Okay. So first of all, we start with the composite trapezoid rule on the interval 1 and 2. And of course, if we have if we have 4 panels, it means that h is going to be equal to 1/4, right? So then if we do so, the approximation is going to be h divided by 2, which is 1/4 divided by 2, times y0 plus y4 plus 2 summation of from 1 to 3 of yi. So this is going to be 1/4 divided by 2, 1/8, and then this is going to be log of 1, which is the lower. Log of y4 is equal to log of 2, which is the upper, and then 2 times, if you think about it, so 4/4 is equal to 1, and then 1 plus 1/4 is going to be 5/4. 5/4 plus 1/4 is going to be 6/4, and then 6/4 plus 7/4 plus 1, sorry, 1/4 is going to be 7/4, right? So, and then if we add 1 more, we have 8/4, which is equal to 2. So that's why we are not adding 1 more, because we are actually summing 3 times the subintervals. Okay, and then if we perform this operation, I'm going to confirm it, is log of 1 plus natural log of 2 plus 2 times log of 5 divided by 4 plus 6 divided by 4, well, natural log of 6 divided by 4 plus natural log of 7 divided by 4 of course, and this is going to be equal to this, and then we just multiply for 1 divided by 8, and then we do it, and it's equal to 0.3837. So this is correct. And then once we actually know the results, 1.3837. I don't know if I have the results. No, it's not here. Yeah, the correct value is 0.386294. So, and then we have that this is 0.3837. It's about like 0.0030 away from this correct result. So we have to characterize then the error to make sure that this is actually very close. So then the error is at most, because we do not know actually the fourth derivative. We can calculate it if you want, but it's still more tedious. So what we do then is then approximated by this expression, as I already said, which is just the formula here. So you have 1/6. Of course, you just have to, well, this is the square, 1, and then square, 1/4 to a square, 1/6, no 16th. Then you just take it down here, and then of course we are assuming that the value of 1, which is actually the interval of the approximation square, this is going to be 1 divided by 192, which is equal to, or approximately equal to 0.0052. Okay, so if we check this out, then this is the approximation, or has to be, has to be greater of that 0.38, 37 plus 0.0052. So it's 0.3889. So still we are inside of the interval in interest, okay, with this error. So that's okay. So that's a very simple application. So then we can apply actually the 4th panel Simpsons rule that sets h equal to 1/8. So remember, if this is actually 1/4, and then because we have one more division here, so we're actually having twice the points. So we have here 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9. So I think I missed 1, 3, 4, 5, 6, 7, 8, 9, 10. Yes, I forgot, I missed one. So you have double. So in general here, oops, h is going to be equal to 1/8. So we have in double because we have one more extra point. So the approximation of the integral of the natural log of x from 1 to 2, it's equal to h 1/2 divided by 3, and then y0 plus y8 plus 4 times the summation of from equal to 1 to 2 to 4 of y2i minus 1 plus 2 the summation of I from y2i from I1 to 3. So we can actually substitute those values. So here we go. 1/8 divided by 3, 1/24. This is log of 1, log of 2. Why? Because this is the upper and lower limit. Pretty straightforward. So then we have here the combination. So we have actually if you think about it, we will have all the values from the second step. So we will have 4 times the log of 9/8, because we're having actually after 8/8, which is equal to 1, we're having 9/8. But then we will not have the following one, because the following one is actually the actual interval, and we are actually in the sub interval. Let's say that, and then we're going to have actually the 11/8, natural log of the 11/8, and then the natural log of the 13/8, and plus the natural log of the 15/8. These are the intervals that we have inside of the approximation. This one, this one, this one, and this one. For example, just let's say that we are assuming this as true, right? So it's here, it's here. So we are here. So this is clear because there are 4 points inside of the each. Well, there is one. There are 4 sub intervals, and then we have to add up the overlapping part of the sub intervals, which is which one? So if we have that is actually 4 quarters, well, in this case, actually, we move it from here. So 10/8, 10/8, 10/8 is equal to how much? To 5 quarters. Then we have natural log of 12/8, which is equal to 6 quarters. And then we have the 14/8, which is 7 divided by 4. And then we complete the integral. So then we obtain, at the end of the addition of all these numbers, we obtain the approximation of 0.30x6292. So if we compare it with the value, the real value, so we see that actually we have 5 decimal points correct. So we see now that in general, but not always, the best way to have a numerical integration is actually the Simpsons rule. Okay, And of course, we still need to quantify the error of this. And then there is going to be b minus a h fourth divided by 180 times the fourth derivative, which in general is actually, as we said, 1/8 is the interval to the power 4. B minus a is equal to 6, and then divided by 1/8. And this is the term that we just approximated to 1. And the error is going to be equal to 0.444444. Why? Because remember that the distance between this one is the interval here, 0.5, and then we have that this is 0.00008. That's why we have actually 5 correct terms here. You think about it, because this is 5 times zeros. Okay, so this is how we use the composite rules of the Newton-Cotes approximations. There are both two approaches, the trapezoid and the Simpsons Rule, and in general we can conclude that the Simpsons Rule is actually more sophisticated than the first one, the Trapezoid Rule. And then finally we have the assignment 15, which is actually what we already know as the 2-point forward differences, 2-point forward differences here, and then the 3-point center differences. And then for the second derivative, we have 2 more examples. This is what we saw in the first part of the class. And for the second part of the class, I have 3 exercises, only 3 exercises. Don't do this one. I just crossed it out because we didn't see the composite midpoint rule, but you need to do actually this first, third, and fourth exercise that you already know how to do it. So it's not work, because here we have to do for m equal to 1, 2, and 4 panels. So there is not only, don't do this like 1 for this one, 2 for this one, and 4 for this one. No, for each of these exercises, you have to use 1 panel, 2 panels, 4 panels. For this one, you have to use 1 panel, 2 panels, 4 panels. And for the last one, you have to use 1 panel, 2 panels, and 4 panels. Lo voy a decir en español. Para cada una de las derivadas tienen que utilizar un panel, 2 paneles, 3 paneles. Por supuesto, para un panel es equivalente a tener solamente ¿cuál? La regla básica de los trapezoides y del Simpsons Rule, ¿ok? For m igual a 1, pero ya para 2 y para 4 ya es diferente. Entonces son suficientes ejercicios porque prácticamente tienen 9 ejercicios aquí. Bueno, tienen 3, 6, 9 en uno. Aquí tienen en este caso aplicar el Composite Rules here. Tienen otros 9 ejercicios aquí. Y por último también tienen en este caso que calcularlos de forma similar. Se van a dar cuenta que estas son un poquito más complejas. Estas son muy sencillas, pero son un poquito más complejas. ¿Ok? Para este ya tienen experiencia porque hicimos el ejercicio anterior, entonces ya saben el resultado, pero prácticamente la integral es muy sencilla. Entonces, estas son las tareas para la última tarea del semestre, entonces tarea 15. Entonces lo pueden ver y practically this is all what we need to do. Remember, next week we have the catch-up week, so be aware that you still have time to do what you have to do, and please continue with the great work you're doing. I'll see you next week, and see you with all your assignments that you have left. Thank you very much for coming. I'll see you later. Have an excellent day, guys, and bye-bye. Peace out. I want to stop just the recording. We stop it.